In this video, we will talk about bases and dimension. And the first thing we will do, we'll be talking about the span of a set. So if you have a set of vectors, its span is all the linear combinations of those vectors. So when I use the colors as an analogy for vectors, if we have a set of colors, those are our vectors, we can ask what colors can we make from those basic colors? What colors is in the span of those vectors? So in other words, if you have yellow and blue, those are your two vectors, the span will encompass all the mixtures you can make with yellow and blue. We'll move on to the idea of a minimal spanning set, and that's if you are going out somewhere and you want to take the smallest subset of paints that you own, but you want to be able to cover a certain set of colors. So if you want to say be able to have all the colors, then your minimum spanning set is going to have to be red, yellow, blue. If you only want to cover the cool spectrum of colors, you're going to have a different minimum spanning set. And the minimum spanning set is actually a basis. And so that leads us into the definition of a basis. And a basis is a linearly independent spanning set for your vector space W. So again, it's this basis is linearly independent, and it spans W, and it also is the minimum spanning set. It's the minimum number of vectors you can get away with to construct everything in W. And then last, we'll talk about dimension, which is simply if you have a vector space W and you have a basis that has P vectors in it, then the dimension of W is equal to P. And we have this very useful theorem here that says if you have P linearly independent vectors, then W is a basis for W. And if you have P vectors that span W, then those vectors are a basis for W. And these two parts of this property just means if you know the dimension is equal to P, then the right number, and the right number being P, so the right number of linearly independent vectors will be a basis, and the right number of spanning vectors is also a basis. So we'll start looking at these ideas in a little more detail. Also, these two examples I have here will be covered in this video. One additional note, when we talk about spanning sets, it's actually a review of what we had covered in my previous video. However, for the review, I do have some new examples. To review spanning sets, so if W is a subspace of Rn, and S is the set of vectors W1, W2 up to Wm, and it's a subset of W, we say that the set S, the set of vectors, is a spanning set for the subspace W, or we can also say S spans W, if every vector in W can be expressed as a linear combination of our spanning set. Another way to express this or denote this is span of S is equal to W. For Rn, and in this case we're going to use R3 for illustrations, the most obvious spanning set is the standard bases. And if you recall from the last video, the standard bases is just the vectors that have 0 in all positions except at this index here. So E1 has zeros everywhere except in the first position. So here's E1. E2 has all zeros except in the second position. So here's the second position or second row, and this is E2. And E3 has zeros everywhere except in the third position. So E4 will have zeros everywhere except in the fourth position. But now we're talking about R3, so we only have 3 standard unit vectors. Now because any vector V, which will represent as A, B, and C, can be expressed as a linear combination of these 3 vectors, the standard basis is our most obvious spanning set for Rn. U1, U2, U3 is also a spanning set for R3, where U1 is 1, -1, 0, -2, 3, 1, and U3 is 1, 2, 4. To show that U1, U2, and U3 is a spanning set, we must show that an arbitrary vector in R3, so we'll just name it with A, B, and C as coordinates, can be expressed as a linear combination of U1, U2, U3. In other words, x1, where x1 is a scalar, times U1 plus x2 times the vector U2 plus x3 times the vector U3. And to figure out if A, B, and C can be written as a linear combination of U1, U2, U3, we just need to solve the matrix equation of AX equals V. So V is our arbitrary vector in R3, and the matrix A is just the column vectors U1, U2, U3. Once I have this augmented matrix, I find that it is row equivalent to the matrix 1, negative 2, 1A. The next row is 0, 1, 3, A plus B. And the last row is 0, 0, 1, minus A, minus B, plus C. And what we get from this, and here I'm just going to notate again, this is for x1, x2, x3. What we get from this, at the bottom, we have x3 is equal to minus A, minus B, plus C. Here we have x2 plus 3x3 is equal to A plus B, or x2 is equal to minus 3x3 plus A plus B. And last we have x1, and I guess since I moved it over, is equal to A, and then moving this over to the other side, I'll have plus 2x minus x3. And I can see then that for any vector, when I have an A, B, and C, I can then solve for x1, x2, and x3. So every vector in R3 can be expressed as a linear combination of U1, U2, U3. I moved what we had on the last slide up here to give myself some more room. So for example, and I chose this vector arbitrarily, but I did choose small numbers because I don't like working with big numbers. So for example, if I just chose the vector 1, 0, 2, I claim I can write that as a linear combination of 1, negative 1, 0, negative 2, 3, 1, and 1, 2, 4. And to solve this, I have my augmented matrix, so I have my 3 column vectors, and then I have the 1, 0, 2 here at the end that I want to solve for. I do my row reduction, and I end up with the matrix 1, negative 2, 1, 1. The second row is 0, 1, 3, 1, and the last row is 0, 0, 1, 1. So from this last equation, I get that x3 is equal to 1. From this equation, I get x2 plus 3x3 is equal to 1, or x2 is equal to 1 minus 3x3, plugging in the 1 here, I get x2 is equal to negative 2. And up here I get x1 minus 2x2 plus x3 is equal to 1. So I solve for that, plugging in the 1 and the negative 2, and I get x1 is equal to negative 4. So if I have negative 4 times u1, negative 2 times u2, and 1 times u3, I get back my vector 1, 0, 2. Here is one more example. Do the vectors v1, 1, 1, 0, v2, 1, 1, 1, and v3, 0, 1, negative 1 span R3. So the question is, can an arbitrary vector v, represented by ABC, be written as a linear combination of v1, v2, and v3? In other words, does this matrix equation, where I have the v1, v2, v3 as the column vectors in my matrix A, x, equal ABC, have solution? So here I have my augmented matrix 1, 1, 0, A. The second row is 1, 1, 1, B. And the last row is 0, 1, negative 1, C. You can see I do these row reductions until I get 1, 1, 0, A. Second row is 0, 1, negative 1, C. And the third row is 0, 0, 1, B minus A. And I hope you have a matrix reducer for you that does this automatically, because when I do this, I only show you once I get the final answer. I have so many errors because I can't add, I guess. Anyway, but here is my row reduced matrix. So just looking at x1, x2, x3. What this tells me is that x3 must equal to b minus a, x2 minus x3 is equal to c, or rewritten, I have it this way, and x1 plus x2 is equal to a. So I have this rewritten. So given any a, b, and c, you can always find an x1, x2, and x3 that satisfies this condition. So for example, again, I just choose a small vector, a vector with small numbers, just to do kind of a sanity check. By no means is this a proof that your equations work, but it kind of gives you a good feeling. So for example, 1, 2, 3, I plug in for x1, 2a is 2 times 1, minus b, which is 2, and minus c, which is minus 3. and I get x1 is equal to minus 3, x2 is equal to 4, and x3 is equal to 1. And you can see that 1, 2, 3 is equal to minus 3 v1, 4 v2, plus v3. So these three vectors, which for some reason I named as u1, u2, u3, but it's really v1, v2, and v3, do span R3. In contrast, I'm going to give you an example where the vectors do not span R3. So we have v1 is equal to 1, 1, negative 2, v2 is equal to 2, 5, 2, and v3 is equal to 1, 3, 2. Do they span R3? So again, we have our arbitrary vector v, which is equal to a, b, and c. Can that vector be written as a linear combination of v1, v2, and v3? Can that equal to a, b, c? So in other words, does our matrix equation A, where A, the matrix is just the column vectors v1, v2, v3 times x equal a, b, c have solution? So I have my augmented matrix 1, 2, 1a, the second row 1, 5, 3b, and the last row negative 2, 2, 2c. You can see my row reduces to 1, 2, 1a. The second row is 0, 3, 2, b minus a. And the last row is 0, 0, 0, minus 2 plus 4a plus c. And these zeros tell you something's up because this only has solution when 0 equals minus 2b plus 4a plus c. In other words, when c is equal to 2b minus 4a. So only vectors of this form, where we have an a, a b, I guess I should write this, only vectors of the form a, b, 2b minus 4a have solutions. So in other words, once we row reduced, we have a restriction on which a, b, and c's will have solutions, only vectors of this form. So I gave you an example. So for example, let's say a is equal to 1, b is equal to 0, then c must equal to 2 times b, which is 2 times 0, minus 4a, which is 4 times 1, is 1, 0, 4. So this has solution. Looking back over here, I see that x3 can be free. So I'm going to just take x3 equal to 0 because that's easy to compute. That means x2 and then x3 is equal to 0. This term goes away, so 3x2 is equal to b minus a. So in other words, x2 is b minus a. In this case, b is 0, a is 1. So we have a minus 1 divided by 3. So x2 is equal to minus 1/3. x1 is equal to a minus 2x minus x3. So I plug those numbers in and I get x1 is equal to 5/3. So I see that 104 is equal to 5/3 times v1. And where's x2? Minus 1/3 times v2 and 0 times v3. So I see that 104 can be written as a linear combination of the three vectors because 104 is of this form. However, if I just choose an arbitrary vector that does not suit this form, like 1, 1, 1, obviously here c is not equal to 2b minus 4a, it doesn't meet this criteria, so 1, 1, 1 is not in the span of v1, v2, v3, and therefore v1, v2, v3 do not span R3. Now we can talk about minimum spanning sets. So the idea is once you have W, it's a subspace of Rn, then the spanning sets for W abound. For example, if a vector v in a spanning set can always be replaced by AV, where A is a scalar. The easiest example of this is we have our standard basis that spans R3. We can just multiply everything by 2 and we'll still have a spanning set. These will still span, just that your coefficients x1, x2, and x3 will have to be decreased by half. And also, I didn't even have to multiply all of these vectors by 2. I could have just multiplied the last vector. So that 1, 0, 0, 0, 1, 0, and 0, 0, and I can multiply it by 1/2. Also spans R3. So it turns out for any vector space, there are many spanning sets, but we are concerned with finding efficient spanning sets. And it turns out if you have a linearly dependent set, they're inefficient because linearly dependent sets contain redundant information. And again, the idea of finding an efficient spanning set is that later when you want to write your vectors in terms of your your vectors, your spanning vectors, you only need to find 3 coefficients instead of like 5 because you have a linearly dependent set. And the other thing, just in terms again of kind of a nice fuzzy feeling, is like if your vectors are colors and you're going out and you can't take, if you want to have a million colors in your painting, you don't want to take a million colors. You want to take the smallest number of colors that then you can mix together to make your million colors. So you're looking for an efficient set of paints that will suit your needs, the color palette you want. For example, we know that E1, E2, E3, the standard basis for R3, spans R3 because for any vector V, where V is given by V1, V2, V3, we can write V as a linear combination of E1, E2, and E3 by writing it as V1 times E1 plus V2 times E2 plus V3 times E3. But we can also show that the vectors E1, E2, E3, in addition to 1, 1, 0, also spans R3. One, that's obvious because these 3 span on its own. And maybe you find this extra vector convenient. So for example, if you wanted to make 2, 2, 0, you can make it just from the one vector, 2 times 1, 1, 0, this vector here. But you can also just make it from 2, 1, 0, 0 and 2, 0, 0, 1, the standard bases. So it's kind of like, well, if you have a set of paints and you're always using the color purple and you want to make dark purple or light purple, then maybe you want to carry your purple around because you always use it and it's super convenient just to have purple instead of always having to mix red and blue and then figure out your purple. But again, if you want a minimum set, you can get rid of purple. You can get rid of 1, 1, 0. So again, the 1, 1, 0 is essentially redundant because 1, 1, 0 can be made from 1, 0, 0 and 0, 1, 0. So it's not part of an efficient spanning set. And now we are ready to talk about a basis. So a basis for W is a linearly independent spanning set of W. So the 2 components of a basis is it's linearly independent and it spans. And so the idea is that a basis is an efficient way to span the set. So we discussed how the standard basis is the obvious basis for Rn, so E1, E2, E3 is the obvious basis for R3, and we also saw these 3 vectors, 1, 0, 0, the second vector 1, 1, 0, and the last vector 1, 1, 1. We showed in a previous example in this video that they span R3, so I have repeated the calculations here. So we know they span, and I also now have the calculations to show they are linearly independent. To show they are linearly independent, we look at the homogeneous equation, which is the first vector times x1, the second vector times x2, the third vector times x3 is equal to 0, 0, 0. And we find that only the trivial solution works. So that makes these 3 vectors linearly independent. So the 3 vectors span, they're linearly independent, and therefore they are a basis for R3 as well. So for any vector space, there are multiple bases, and some bases are nicer than others. One example that we will not be covering in this series of videos are the orthonormal bases. They're super nice. But anyway, there are many bases, and here you see 2 examples for R3. Another example, let W be the subspace spanned by S, and we have 5 vectors, 1, 1, 2, negative 1, 1, 2, 1, 1, 1, 4, negative 1, 5, 1, 0, 4, negative 1, and 2, 5, 0, 2. We want to find a subset S that is a basis for W. To start, to find a basis, we need to have 2 things. We need our set to span, and we need them to be linearly independent. Well, by definition, this set, the set of 5 vectors, will span the space we are interested in, so we need to find a linearly independent subset of these 5 vectors. To winnow down these 5 vectors to a set of linearly independent vectors, we solve the homogeneous equation. In other words, we set x1 v1 plus x2 v2 plus x3 v3 plus x4 v4 plus x5 v5 equal to 0. So my augmented matrix is my matrix with v1, v2, v3, v4, and v5 times x equals 0. So here is my augmented matrix, which is 1, 1, 1, 1, 2, 0. My second row is 1, 2, 4, 0, 5, 0. My third row is 2, 1, negative 1, 4, 0, 0. And my last row is negative 1, 1, 5, negative 1, 2, 0. And that is row equivalent to this matrix here, 1, 1, 1, 1, 2, 0, 0, 1, 3, negative 1, 3, 0, 0, 0, 0, 1, negative 1, 0, 0, 0, 0, 0, 0, 0. Because of this, we have essentially x3 and x5 are free because we have 1, 2, 3, 4, 5 variables, x1, x2, x3, x4, x5, but we only have 3 non-zero rows, so that must mean 5 minus 3. We have 2 free variables. And then here we have, let's see what we have, x1, x2, x3, x4, x5. So our top equation tells us that x1 plus x2 plus x3 plus x4 plus 2x5 equals 0. And I rewrote that equation. x2 plus 3x3 minus x4 plus 3x5 equals 0. And x4 is equal to x5. So plugging in, this is my solution. And now I'm going to look at x3 and x5 separately. And by that, I mean first I'm going to set x5 equal to 0 and x3 equal to 1. So that will allow me to focus on x3 because I set x5 equal to 0. And then the next step, I'll do the opposite. I'll set x3 equal to 0 and x5 equal to 1 so I can focus on x5. When I set x3 equal to 1, x5 equals to 0, I get x1 is equal to 2, just using this equation here. x1 is equal to 2, x3, so I get 2. x2 is equal to negative 3, and x4 is equal to 0. So when I plug this in as a linear combination of my v1, v2, v3, v4, v5, I get 2 times v1 minus 3 times v2 plus 1 times v3 plus 0 times v4 and 0 times v5. So I'm left with this equation, so I can solve for v3 in terms of v1 and v2. And I could have chosen to solve for v2 in terms of v2 and v3, but here's v3 without a coefficient, so I thought that was easiest. Now when I solve for x3 equals 0 and x5 equals 1, I get x1 is equal to negative 1, x2 is equal to negative 2, and x4 is equal to 1. So I have my negative 1 v1, my negative 2 v2, 0 v3, 1 v4, and 1 v5. So I solved, and this time I chose to solve for v5, and I get a linear combination. v5 is a linear combination of v1, v2, and v4. And since I have v3 and v5 solved in terms of v1, v2, and v4, that means v1, v2, v4 can be my bases. So I eliminated the redundant vectors v3 and v5. And just a note, there are other ways to find bases that depend on you knowing the range and the null, the rank and the nullity, which those topics we skipped. So I cannot, I chose to skip them, so there are other ways of finding bases. Now that we've talked about bases, we're ready to discuss dimension. If we have a vector space W, and W has a basis of p vectors, then we say that W is a subspace of dimension p, and we write dimension W is equal to p. In other words, the dimension of W is just equal to the number of vectors in the basis. And just to be clear, we have this theorem in corollary, which tells us that if we have a subspace of Rn and we have a basis with p vectors, then every basis of W contains p vectors. So you're not going to get one basis with p vectors and another vector basis with p plus 1 or p minus 1 vectors. All your bases are going to have the same number of vectors, which is how we can define dimension. And we have this nice property for a p-dimensional subspace. So let W be a subspace of Rn with a dimension equal to p, then 1, any set of p plus 1 or more vectors in W is linearly dependent. And if you think of a basis as the minimum spanning set, then it shouldn't surprise you when you add one more vectors, you're going to get something that's linearly dependent. The second property is any set of fewer than p vectors in W does not span W. And again, if you think of the bases, which has p vectors, as the minimum spanning set, that tells you if you take one away, you can no longer span W. And what follows are these two results, which is really nice. So if you have p linearly independent vectors and the dimension of W is p, then you know these p linearly independent vectors is a basis. You don't have to go and show that they span, because basically the right number of linearly independent vectors will be a basis, and the right number is the dimension. Similarly, any set of p vectors that spans W is a basis for W. Again, if you know that the dimension is p and you have a set that spans, you then don't have to show they're linearly independent, because the right number of spanning vectors will be a basis, and the right number is p. Two more examples and I think we're done. So let W be the subspace of R3. Defined by W are the vectors x such that we have x1, x2, x3, such that x1 is equal to minus 2x3 and x2 is equal to x3. Exhibit a basis for W and determine the dimension of W. First, we want to look at what these x's look like. So I wrote an x1 and x2 are in terms of x3. So I have x3 here. I have x2 is equal to x3. So here I have the second coordinate equal to x3. And our first coordinate is equal to minus 2x3. So I have that here. And now I can pull out my scalar multiple x3, and we see we have minus 2, 1, 1. So any vector of this form, any scalar multiple of minus 2, 1, 1, fits this description. And in fact, only scalar multiples of minus 2, 1, 1 fits the description here. So in other words, the span of W is equal to negative 2, 1, 1. And there's only one vector, so negative 2, 1, 1. This one vector is linearly independent, and therefore negative 2, 1, 1 is a basis for W, and the dimension of W is equal to 1. I lied, there are two more problems. So this is the second to the last problem. A little bit harder. Find the basis for the subspace span by U1, U2, U3, and U4, where U1 is 1, 1, 2. U2 is 2, 4, 0. U3 is 3, 5, 2. And U4 is 2, 5, negative 2. So we want to find a basis for W and the dimension of W. First to note, since W is a subspace of R3 and the dimension of R3 is 3, we know the dimension of W has to be less than or equal to 3. To start, we need to know what W looks like, what the vectors in W look like. So in particular, if V is in W, then V is a linear combination of these four vectors, right? Because the W is the space spanned by the four vectors. In other words, V is the vector A, B, C, such that we can write this vector equation, our U1, U2, U3, and U4 as the column vectors of matrix A times V1, V2, V3, V4. These are our coefficients, which will equal to A, B, and C. That's our vector V. So solving the augmented matrix, which is 1, 2, 3, 2A. The second row is 1, 4, 5, 5B. And the last row is 2, 0, 2, negative 2C. That's row equivalent to 1, 2, 3, 2A. The second row is 0, 2, 2, 3, minus A plus B. And the last row is 0, 0, 0, 0, minus 4A plus 2B plus C. And what this tells us of our vector V's are the vectors A, B, C, which satisfy this restriction that 0 is equal to minus 4A plus 2B plus C. So I write that here, that V are the vectors that have A, B, and C, the last coordinate, is equal to 4A minus 2B. So here I have the last coordinate is equal to 4A minus 2B. So I separate this out, and because I want to separate out my A's and B's, so I separate this to A0, 4A, plus here I don't have any B terms, so 0B minus 2B. So these two vectors added together give us V. And now I can pull out my scalars, and remember, A, B, and C are just the coordinates of V, so they're scalars. I can pull them out, and I got 1, 0, 4A plus 0, 1, negative 2B. So this is the general form of the vector V. So in other words, it's 1, 0, 4 multiplied by a scalar, and the vector 0, 1, negative 2 multiplied by a scalar. So all the vectors v are linear combinations of the vectors 1, 0, 4 and 0, 1, negative 2. And therefore, w has a basis of 1, 0, 4 and 0, 1, negative 2. And you can also see that they are linearly independent because they're not multiples of each other, since there's only two of them. And the dimension of w is then equal to 2. Here we have our last problem using the same vectors from our last example, that u1 is equal to 1, 1, 2, u2 is 2, 4, 0, u3 is 3, 5, 2, and u4 is 2, 5, negative 2. We can consider the vectors v1 is equal to 1, negative 1, 6, v2 is 1, 2, 0, and v3 is equal to 2, 1, 0. We want to determine which of the subsets, v1 by itself, v2 by itself, or v1 and v2 together, or v1, v3 together, or v2, v3 together, or v1, v2, v3 is a basis. In other words, we're looking at all possible combinations to see which one could be a basis. Previous example, we find the dimension of w is equal to 2. And by our properties here, basically we need the right number of spanning vectors to be a basis, or a right number of linearly independent vectors to be a basis. So our basis has to have two vectors. So that eliminates just one vector by itself, or three vectors. So the only candidates really are v1, v2, v1 and v3, and v2 and v3. So here are our three candidates. So v1 by itself, v2 by itself, v3 by itself. By this property here, any set fewer than p vectors does not span. v1, v2, v3, they will not span by themselves, so it can't be a basis. Here, when we consider v1, v2, and v3, so at this point, dimension is equal to 2. So any 2 plus 1, 3 or more vectors is linearly dependent. So these vectors, v1, v2, v3, must be linearly dependent, so they also cannot be a basis. And I'm just going to say you can verify v1, v2, and also the set v2, v3, and the set v1, v3 are all linearly independent, so they are all bases. In this video, we reviewed spanning sets, and the idea of a span of a set of vectors is it will be all the linear combinations of that vector. If we go back and consider vectors as colors, if we have a set of colors, the span is all the colors we can make from our vectors, from our colors. We also talked about minimum spanning sets as far as bases. So if you have a set of vectors that you want to span, you can do that using a basis, and that will be your smallest spanning set. And a basis has two conditions. One, it spans your set, and two, it's linearly independent. So in terms of color, if you want to be able to access all the colors, then you want to span all the colors, but you want to do it with as efficiently as you can with the smallest set of colors. You want to only pack a few colors, but you want to be able to make all the colors when you're going to paint. So you want linearly independent colors. So you don't want, say, green, because you can make those from yellow and blue. You only want the colors you can't make from other colors. In that case, your linearly independent set would be red, yellow, blue. And so the bases are particularly nice because they give you the minimum number of vectors that you need to cover exactly what you want. Last, we talk about dimension, and once you have a basis for a vector space, there are actually many other bases, but they're all going to have the same number of vectors, and that number of vectors is called the dimension. And then we have these properties here that, as we saw in our last example, can be really useful. So that's it for this video. Thank you for watching.